Alright, so here's your video lecture for Chapter 4, Section 2, entitled The Quantum Model of the Atom. We're going to start off by talking about Louis de Broglie. Did some work in 1924, among other things. What we are going to talk about is the fact that he applied the wave-particle theory, specifically the wave part of that theory, to the electron, because he noticed that the electron in Bohr's model of the hydrogen atom shared several characteristics with waves. Now, the fact that he was thinking of was any wave that exists in a confined space can only have certain frequencies, and we'll look at a diagram next slide. But that is a fact about waves that Louis knew for sure. But when he was looking at Bohr's model of the hydrogen atom, he noticed that electron in the hydrogen atom is confined to a certain space. It's the electron cloud. Therefore, it can only contain certain frequencies because it inhabits discrete energy levels, just as Bohr described. So here, again, we're laying that foundation of electrons as waves. De Broglie, again, waves in a confined space. This is a very common example used, the string of a guitar. And we all know that when you strum a guitar, those guitar strings will vibrate, and they will vibrate, and you will see half wavelengths as they vibrate. Now, it's important to note here you can have one half length, okay, wavelength divided by 2, it's a half wavelength, 1 in front. All right, that's a 1/2 wavelength. You can see that this is completely okay. Okay, in these situations and the 2 half lengths, that the half wavelength completes perfectly within the circumference of a circle, and so that's completely fine. That frequency can exist. But once you get to a certain point, a certain half wavelength, or a certain number of your half wavelengths, the wavelength path will not complete. It will go too far or will not go long enough, and that continuous wave will not be formed as that, in this case, electron moves around the object. So we have, if you can have an N or an energy level of 3, that's fine because the wavelength, the wave path completes. If you have n equals 5, that's okay too, but 3.3, that doesn't work. Scientists demonstrated that electrons can be diffracted and can interfere with each other. Before we talk about what that means, let's talk about those two words. Diffraction is the bending of a wave as it passes by the edge of an object. Interference occurs when waves overlap, which results in the reduction of energy in some areas and an increase in energy in other areas. So with those in hand, the evidence that Louis had was diffraction patterns. Diffraction patterns, going back to that definition of diffraction, it's the bending of light as it passes by the edge of an object, and interference, okay, it's when waves overlap, they decrease in energy so that you actually can't detect them, and then in other areas they increase in energy because the peaks have summed together, and so there's an increase in energy and an increase in the amplitude. So here is an example of diffraction patterns that we see in visible light. This is visible light moving through an aperture, and you can see the interference pattern. You can see the area of intensity alternating with areas of nothingness. This is a trough area, okay, where there's the amplitude is 0, and then a very high amplitude right here. This is an interference pattern here, and if we compare that to light move through an electron, we see a very similar pattern. We still see that diffraction and an interference pattern. What's the conclusion here? Electrons are waves. Alright, so let's see what we have so far here. Go ahead and pause the video and check to see how you're doing. Hopefully you selected A right there. Only the wave theory of light offers an explanation for the ability of light to exhibit interference. A reflection, photoelectric emission, or the intensity of radiation is not explained by the wave theory. Either that or it is not only explained by the wave theory. Go ahead and pause the video one more time. The photon or particle model of light is more appropriate than the wave model in explaining photoelectric emission. Okay, we talked about the photoelectric effect, talked about photons interacting with the atoms in a metal plate and causing electrons to be ejected. So that photoelectric effect depends more on the photon or particle nature of light. So that's different than what Louis de Broglie was investigating. Pause the video one more time. Alright, I hope you selected A. Interference and diffraction can be explained by wave theory only. Okay, we're just talking about waves. Interference and diffraction are both properties of waves. One more time, pause the video. Alright, I hope you selected B there. Louis de Broglie was able to conclude that electrons also behave as waves because waves in a confined space have certain frequencies. Alright, that was one of the things that led him to do his investigation. Moving on, you have the Heisenberg uncertainty principle. Now this is the idea that electrons have wave and particle nature. But that bothered scientists at the time, around the 1920s. So Heisenberg proposed an idea that involved the detection of electrons, how you observe electrons. Now the Heisenberg uncertainty principle states that it is impossible to determine simultaneously both the position and velocity of an electron or any other small particle. Now he's not saying that you cannot determine the position and you cannot determine the velocity, you just can't do them at the same time. And we have down here at the bottom the actual mathematical expression for the Heisenberg uncertainty principle. And I'd like to remind you, in class we talked about that delta x and that delta p, the location and the momentum, being multiplied by each other, making them inversely proportional once their value becomes small enough to put this equality value in danger. Moving on to Schrödinger's wave equation, Erwin Schrödinger used the idea that electrons act as waves and particles, and he developed an equation to describe the wave nature or wave characteristics of electrons. Combining this equation with Heisenberg's uncertainty principle is essentially the foundation for modern quantum theory, these two things together. In quantum theory, the uncertainty principle and Schrödinger's wave equation, they both describe mathematically the wave properties of electrons as well as other very, very small particles. You might hear someone say particles on the quantum scale, simply meaning extraordinarily small, about the size of a proton or an electron even. Now a little bit about the wave equation specifically. Because there's a finite, which means there's not an infinite, it's a certain, and it's a somewhat small number. Because there are a finite number of solutions to his equation, that fact helped confirm the quantized energy levels of electrons. The fact that there are only certain solutions and there turned out to be frequencies confirmed Bohr's idea of quantized energy fields in electrons. So functionally, this equation defines the probability of finding an electron at any particular location. Typo right there. All right, let's see how we're doing. Go ahead and pause the video and see if you can answer this question. I hope you selected D. You can never know one and the other simultaneously. So Heisenberg's uncertainty principle states that you cannot know location and momentum at the same time.